me upload it, then I'll give you at least 2 weeks.
Okay, okay, sir. Thank you, sir.
Because this time we don't have, usually we used to have the Dasara break, a 1 week Dasara break. This time we don't have a Dasara break, right? You might have noticed that, right? Yeah, so
Yeah,
if you look
yes.
at the calendar, there is no Dasara break. So usually Dasara break used to be kind of a buffer which I could count in when I'm giving you the project. I'll usually ask students to use that Dasara break to complete the project. But this time that break is not available. So I'll try to upload it maybe today or tomorrow at latest. If I don't upload it, just somebody can remind me. Okay, by weekend, if you don't see the project uploaded, just remind me, send me a message. Fine, then I'll try to give you at least 2 weeks to work on. This, I think, is a 40-meter tall tower. If I can look at the Z, Y values. Yeah, no, 25-meter only. Okay. Only 25-meter tall. No, 40 actually. Yeah, 40 meters tall. So for the time being, please try installing the software. If you don't have StatPro with you already, please install it and see if you're able to work with it easily. Fine. So in the previous class, we were talking about angle sections which are in compression but are connected with only one leg. Correct. So then we had mentioned that since these are connected with only one leg, we definitely are going to have an eccentricity, and that eccentricity will force it. So any section which has, so if it has an eccentricity, the two flexural modes of failure are completely impossible. So then the code actually makes you consider the three possible combined modes of failure. The modes are two flexures and one torsion. So instead of two flexures, basically the one flexure that is the weaker flexure, that one, and torsion, and then basically you get an effective slenderness. So basically the code does not ask you to consider the flexural torsional buckling about three different axes. It just asks you to consider one flexural torsional buckling, which is a combination of flexure in weak axis and torsion. Okay, and then these are the expressions. These are all formulae are given to you. You use these, the K1, K2, K3 factors you have to use in this one to get the effective slenderness, and then you use the same equations which were actually developed for flexural buckling. Okay, so only what we are doing is that in that flexural buckling equation, we are substituting the value of lambda for the equivalent slenderness, which accounts for the flexural torsion. So this is not really a very principally or theoretically very sound method. This is very, very empirical method, because ideally the equation itself should have changed completely, correct? But and if you look at some of the other international codes, for example, if you look at the American code, there they have a completely different equation for the column buckling itself, or angle buckling itself, okay, when it is subjected to compression, which is eccentric. However, in the Indian code, we have adopted a different approach. Now, this is not theoretically sound, but it does not mean that it is not good. Okay? Basically, whether an equation or any formula that is given in the code, whether it is good or not, depends on its accuracy of prediction. So if it predicts the capacity accurately enough, conservatively enough, then it's good. Okay. Now, a couple of other important subtopics of the same angles under compression we will discuss today. So oftentimes what happens is that angles are provided as double angles. They are not provided as a single angle. And that thing you can see in towers sometimes, but more than towers, you see this thing happening in roof trusses, right? So in a roof truss, for example, when you have a so in a roof truss, for these members, it is very common to go with a double angle system. So basically what is happening is that you would have some gusset plates here sitting here at the corners. Likewise, if the members are something like that, if the truss looks somewhat like this, then you would have some kind of a gusset plate here, some gusset plate here, gusset plate here, and so on. So in such a case, what will happen is, let's look at this corner. So you have a gusset plate, and this member will be here. Which will often be made of one angle going this way, and then the other angle right behind it. And the gusset plate will be sitting right in the middle of the two angles, sorry. Okay, you get it, right? So between the two angles, there will be a small gap, and the gusset plate will be sitting between the two. So you can see this arrangement here. So this top member, it could sometimes be at the bottom also, but at the bottom usually the member is in tension, and the member strength typically in tension is much higher than its strength in compression. So that is not as common, but sometimes you will see that. In compression, it is much more common. So in compression side, you will see these double angles being used, one on each side of the gusset plate. Okay, and sometimes the double angle could be used one on each side of the gusset plate. Sometimes double angle also can be used in such a way so that it is both angles are on the same side of the gusset plate. Okay, so for example, here you have one double angle on each side of the gusset plate. This is another one on each side of the gusset plate. This is another one. But also you may have some kind of a situation where this could be my gusset plate, and then let me first draw the numbers. Okay. So these are two angles back to back, placed on the same side of the gusset plate. Okay, you can visualize it, right? So looking into this direction, this will look like one angle, other angle, sitting on the gusset plate. Okay, and these could be welded or bolted, any kind of. So whenever we have two angles, if we want to call them double angle, okay, we have this kind of an angle arrangement. Sometimes we may have them back to back of a gusset plate, like on the either side of the gusset plate, or sometimes we may have on the same side of the gusset plate. Either case, what is most important here is that the angles, the two members, should be stitched together at regular intervals, and there are provisions for that, how close the interval has to be. Basically, what it means is that you have these two angles going along. At every few inches or millimeters, you have to stitch them together. You have to. So any plate that is joined or that is common between the two angles. Likewise here, so these are the two angles going in this direction. They have a gap in between, but irrespective of whether you have a gap between the angles or not, you have to stitch them together. Okay, and how do you stitch them together? Mostly you put a bolt through them. Okay. So you have these two angles. Again, here also, you have to make a way. You have to make a provision so that the two are bonded together at regular intervals. Similarly, these also. Okay. And you don't have to tie this leg with this leg. As long as you tie one leg that is almost abutting each other, that is good enough. Fine. So why do we need to stitch them together?
To act as a single member.
What happens if we don't stitch them together?
They will act independently.
Yes, so they can bend independently. So there, what you will get as a result, basically, if one angle's compressive strength, let's say, you calculate using the formulation given here, it turns out to be something. You use two angles, you will get twice as much strength only. Okay, but if you stitch them together, then how much strength will you get? Multiple times higher, because then what will happen? First thing is, since the gusset plate is sitting between the two between the net cross section. So in this configuration, what it looks like, it will look like this. This is another angle, and the plate is sitting here. So the centroid of the two angle system is somewhere here, right? And the gusset plate is also sitting, its centroid is also somewhere here. So when you are applying the axial load, it is acting right at the centroid. So then the issue of lateral torsional buckling or flexural torsional buckling is resolved. It's not really required. So you can consider this as a flexural system. Pure flexural buckling can be considered. So one is that with a single angle, it had the chances of, because if you look at each angle independently in this system, if you look at each angle independently, this angle would still buckle in the flexural torsional mode that we have just discussed, because it's an angle and only one leg is connected to the gusset plate. However, if you tie them together all the way along, then the total system, it is not loaded eccentrically, but it is loaded concentrically, because now for the total system, the centroid is here, that's where it is loaded. So it can be, then you don't have to consider flexural torsional mode of buckling, you just need to consider flexural mode of buckling about this axis. Fine. So one thing you do is you change the mode of buckling. The second thing that you do is, because they are both combined now, the net I value, modulus of inertia, moment of inertia, or R value, that will be not only twice as high, but much higher than what was available for a single angle. Okay, so I or R, moment of inertia or the radius of gyration, that increases multifold, not just twice. Agreed? It is just like if I have one block, what is the moment of inertia? 1/12 BH cube. Okay, if I bring another block and don't tie them together, what is the total moment of inertia? 1/6 BH cube. Okay, where B is this, H is this. Right? But if I tie them together, then my moment of inertia is 1/12 B 2H cube. How much is that? 8. 8/12, that is 4/6 BH cube. Correct? So instead of 1/6 BH cube, you have got 4 times higher. Right? So it is not just doubling, it is going 8 times higher. Same thing would happen here when you stitch them together, then they will bend together. So that is very, very important. So you stitch at regular intervals in a way so that they bend together. And if they are connected to both sides of the gusset plate, then there are certain set of provisions. And if they are connected to one side of the gusset plate, then there is certain set of provisions. Now, what is the difference between the two possibilities? This is the possibility where they are connected to the two opposite sides of the gusset plate. That is your both sides of the gusset plate. This is the one. The provision number is 7.5.2.1. So this is 7.5.2.1. Okay. And this one, where the two angles, which are double angle system, which is both of them are connected to the same face of the gusset plate, which is 7.5.2.2. So you need to go to the IS 800 and read these provisions. Okay. Now, what it says when it is on the either side of the gusset plate, that is, the two angles are on the opposite faces of the gusset plate. In that case, as I mentioned before, you are changing the buckling mode. Earlier, for a single angle, the buckling mode was flexural torsional, as we had discussed. But when you put two angles together on the either side of the gusset plate, then you bring centroid right where the load is. The load is also acting here, centroid is also there. Then the torsional mode of buckling can be ignored, only flexural needs to be considered. So you can simply consider the situation as a concentric loading, buckling class C under flexural or principal axis. Okay, so principal axis, the one principal axis will be this one, the other principal axis will be this one. Okay, and about these two axes, you measure which one, you calculate about which one it has lower capacity, and then about that one you or longer unsupported length KL. So whichever axis you have a greater KL value, about that one you calculate the capacity using buckling class C formula. Okay. One more thing you have to remember is that in this particular case, you will have a gap between the two angles. The two angles will not be touching each other. Why not? What you see here is this gusset plate, right? So right where the gusset plate is, you have to create that gap because there is a gusset plate in between. And as you move away from the gusset plate, that gap has to be maintained, okay? In order to not introduce any additional stresses in the members. So how do you do that? How do you keep that gap? How do we keep that gap? There is something called
Baker points.
spacer blocks. Okay, and the only purpose that spacer blocks have is to keep that gap, maintain that gap. There are certain advantages of that gap, right? So you have one angle here, the other angle is here, and there is a gap in between that increases your R value or I value about primarily about this axis, right? Your I becomes larger if you keep some gap. So gap is good as long as you can make the two members or two parts of this member behave together or behave coherently. So then what you have to do is in between, wherever you are going to do the stitching, that is, you are going to put one bolt through it, there you have to put a small block which has the same thickness as the gusset plate, which was at the end. So this could be the spacer block, okay, or it could be the gusset plate. So here you had a gusset plate. After some distance, you have to put a small steel plate which has the same thickness as this gusset plate. Wherever you are doing the stitching, there you have to provide that small steel plate to maintain that distance, the gap. Okay, but if they are stitched on the same side, if the two members are stitched or if they are connected to the same side of the gusset plate, in that case, typically you would not have a space in between. So you don't need the spacer blocks, and then you can tie the two legs together directly without having to provide any spacer block. Right? But now in this particular case, if you look here, you have these two angles and the loading is, so where is the centroid of these two angles? Somewhere here. Here is the centroid. Okay, and where is the loading? Here. Fine. So again, in this case, you have the possibility of flexural, torsional buckling. Now, for this particular case, the code gives you a provision to look at 7522, but it does not fully address that issue. So this is left to the designer or to refer to more advanced literature. If I go to 7522, what does it say? Here is 7522. So if it's a double angle, discontinuous strut connected back to one side of a gusset plate or section by one or more bolts or rivets in each angle, or by the equivalent in welding, shall be designed in accordance with 751. What is 751? 751 is this one, loaded through one leg. And the angles shall be connected together over their length so as to satisfy the requirements of, so this requirements of 7.8 and 10.1.2, 10.2.5, these are, both of them are just going to make sure that the two angles behave together. Okay, there is nothing special. This 7.5.1 is essentially saying, asking you to use the provisions of this one. I'll go to 7.51. So 7.1511, it says it's concentric loading, but this, in this particular case, it is an eccentric loading. So you are left with loaded through one leg kind of a provision. Okay, when you go double angle, discontinuous struts connected back to one side of the gusset plate. So now in this particular provision, you are required to put in the values of B1 and B2 and 2T, that is for one angle. But when you have two angles joined together, what kind of torsional resistance it has, it does not really answer that question. So this is relatively not adequately answered. I have seen textbooks where sometimes even this kind of a member, they do not, even this kind of a situation, where they do not consider the torsional buckling and they simply, flexural torsional buckling, they simply go with flexural buckling. So if you decide to do it that way, that is also okay. So flexural buckling, you ignore this eccentricity, even though the eccentricity is there, you can ignore this eccentricity and just go with flexural buckling. But that is not really the best way or correct way to do it. But the kind of code is in a way silent. Okay, it does not specifically spell out in 751 which provision to use. 751 it says. Now my reading is that we should use 7512, but in 7512 this particular expression of b1 plus b2 divided by 2t, it is derived only for a single angle. It is not derived for double angle situation. So in a double angle situation, the torsional constant or torsional stiffness will be different, and we should be given an expression for that, but that is not given properly. Okay. So there are various places where the code is not very does not very clearly spell out what you are supposed to do, and you have to use your judgment, or otherwise you can refer to some specialized literature. So as far as the code is concerned, it is silent. So either approach is okay. All right. Now, if these are the two possibilities. Now, what is the effective length we should take in each possibility? So if it is in this kind of a situation where the two angles are on either side of the gusset plate, and now if this member, let's say this member, which is put in this particular strut, which is inside this ellipse, for this member, if it is connected with one bolt on both ends. So if there is only one bolt provided here between the gusset plate and the member, okay, then what kind of rigidities will it offer? Will it allow it to move a bolt, single bolt, or
It will not allow to move, but it will allow to rotate. That's why they are taking.
Yes. So with a single bolt, it is very easy for the member to rotate at this point. Okay. But again, it will not allow it to move. So then what it says is that you can take 1 times the distance between the bolts. So in your softwares, typically when you do the analysis, what it does is that it takes the center line of this member, center line of this member, center line of this member. Where the 3 center lines meet, or the centroid line, where they meet, that is the location of the node. And when you calculate the total length, you take the length from here, or distance from here to the node on the other side. For this kind of a situation, the code allows you to take the distance between the bolt to the bolt, not from the node to the node. So actually this is the node location. So like I had just shown you the model of a tower. So in that situation, this will be the node location. So typically we will take the distance between the node to node. We won't care about the actual joint location. Okay. But if you want, and that will be conservative if you take node to node distance. But if you want to be more accurate, you can take even distance from bolt to the bolt on the other side. There will be other side of the member. There is also one bolt there. So this bolt to that bolt, that distance you can take multiplied by 1. That is your K value. Okay. However, if you provide more than one bolt, then what happens is that even rotation is restrained. Okay. Even the rotation is restrained. Then what we do? Then it comes down to this gusset plate's ability to rotate. The gusset plate typically does not rotate, or even if this member, it is connected without a gusset plate to a member, that member is not going to rotate because this wants to rotate simply. So in that case, what happens is that the code requires you to take a fixity level of 0.7 to 0.85. It does not exactly spell out what value you should take. You can assess the in-plane fixity. Typically, to be conservative, I will simply take 0.85 if 2 bolts are provided. So 0.85 times the distance between the nodes. From one node here, this is the definition of node. So node is not where the bolt is. This is the location of the bolt. This is the location of the node or the connection. So this is the location of the node or the connection. You may have a welded situation also. And this is the location of the node. Fine. So it says take the distance between the nodes from here to the other end of this member. That total distance times 0.7 to 0.85. I will simply go with 0.85 to be conservative. Okay. Now that is the possibility when we are considering the buckling about which axis? About this axis. Okay. The axis that is parallel to the two flanges, sort of outstanding legs. So this is this double angle. So about this axis, when we are considering the buckling, then we take all that we have discussed just now. But when we are talking about buckling about this axis, can you visualize what will be the buckling? When we are talking about buckling about this axis, this kind of a buckling will make the gusset plate bend. You understand? You agree? So when the angle wants to bend in that direction, buckle in the out of the plane direction. So that is the plane which is, or that is the direction which is perpendicular to the truss. So the entire truss, all the members of the truss are in this plane, but this member is trying to buckle in the out of the plane direction. Okay. So when that is the requirement, in that case, it simply says that since the gusset plate has a very little stiffness in out of plane direction, and you can imagine that the gusset plate will start bending even here if it has to, slightly around this line where it is meeting. So you can simply take k is equal to 1 and take the distance between the nodes. Okay. So take the distance between the nodes and k is equal to 1. So you need to take distance from here to the other end, wherever the node is, and multiplied by 1. Okay, all this makes sense, right? There is no mystery here.
Sir,
How-
I have one.
yeah. Yeah.
Sir, since we attach the angle back to back, so the moment of inertia about that axis will be improved, no, sir?
Yes.
So buckling about that axis, can it happen? Even though a gusset plate doesn't have the stiffness in that axis, but angles.
Good question. Good question. One is that angles need not be equal legged angles. So if you have unequal legged angles, then that is a possibility. You can see that? No?
Yes,
So
sir.
if I have this scenario. So then about this axis and this axis, these could be comparable, right? I understand if you had equal legged angle, then obviously these members are going to buckle about this axis, and this one it will have much higher strength. So this is not very likely, but in this kind of situation, even this is quite likely. Okay, that is one possibility. The other possibility could be, it's a relatively more complex. Let me give you an example. So I have a tower. Okay, in a tower there is a strut like this, horizontal strut. Okay. Now I have provided a lot of braces which are coming like this. So let's say this is the typical configuration of my tower. Fine. Now for this particular horizontal strut, it is, let's say, made of double angle. So typically for a tower to have this kind of a strut, which is a double angle, tower has to be really very tall or very complicated kind of tower, but it is likely still possible. It's not very likely, but still possible. So you have this double angle there for this member. Okay. Now when buckling, the question of buckling comes, it can buckle. What will be the effective length, or let's say what will be the restraint condition here when it comes to buckling? Will these braces restrain its movement up or down? They will, right?
Yes, sir. They will. Yes.
Yes, sir.
Right. So then your length that you should consider is only this much for up-down movement. And then there is another possibility of the member buckling in out of the plane direction. Correct?
Yeah. Yes.
Into the plane. For that one, will these braces offer the resistance?
No.
No. They can only apply forces in the same plane. So no matter how much force they apply, they cannot restrain the movement in the perpendicular direction.
Yes.
So in that perpendicular direction, you have a different length, right?
Yes,
What
yes,
ultimately what matters is KL by R.
Yes, sir.
So even though your R might be higher in one plane, let's say in this case, your R, you have XX and you have YY. Okay. So I know that my RX is less than my RY. Okay. But what I need to look at is just simply this is not good enough. I have to look at KL by R. Right. So just because my Rx was low, it does not mean that KL by Rx will be governing. Okay, because my LX may also be very, very low,
Yes, sir.
just because of the configuration, the way the tower is made.
Yes,
Right?
sir. Yes,
So
sir.
my L can also change.
Yes.
So all those things play out a role. And when you do the tower example, you have to be watchful for such possibilities, where a member is now adding another level of complexity here. I have to draw it in 3D, and I was dreading that. Now I'm looking at this cross section, this particular cross section in 3D. Okay. So these are the 4 corners where the legs are passing. I'm not drawing those legs. Okay. This is that member, which is a double angle member. This member is that double angle, this double angle member. Now I had shown that there are braces coming from the top and meeting here, right? But you may also have a possibility that you have braces here. You may or may not, but you may, right? So if that is the possibility, then these braces will be effectively restraining its movement in out of the plane direction also.
Yes, sir. Yeah.
Then you need to take same L, whether you are talking about buckling about this axis or that axis, if you have both these braces and these braces. You understand?
Yes, sir.
But
Yes, sir.
you may have a situation where these braces do not exist. So if these braces do not exist, then
There is chance of.
yeah, there is a chance of a longer L for that buckling. You have to differentiate between the two. And see, no matter how much I explain in the class, it will become clearer only when you start solving the project problem. Okay, so please pay attention to that. All right, so you may have a situation where this member is continuous. When this member is continuous, you may have a situation like this, a double angle. This is perfect example of what I'm just talking about. This is a double angle member, which is continuous, okay, over a brace, over a braced point. So you may have some kind of a gusset plate here to connect the other 2 braces to this member. Yeah. And this happens quite often in the trusses, cords of trusses. So the compression members of the trusses, that's where you have this kind of a issue, this kind of a possibility. So when it is a continuous double angle, most likely it will be on the 2 sides of the gusset plate. If it is discontinuous, it may be on the same side of the gusset plate, but if it is continuous, most likely it will be on the 2 sides of the gusset plate. It's very unlikely that you will have a continuous double angle, that too only on a single side. So continuous, you understand, right? This is the discontinuous one, and this is a continuous one, right? This is also a discontinuous one. So when it is a continuous double angle, then you need to take, again, the 2 possibilities. It could be buckling in the plane of the truss, or it could be buckling in out of the plane of the truss, right? So this is that angle, that double angle that is continuous. So it can be buckling in the plane of the truss. That means if it has to buckle in the plane of the truss, that means this node will not be moving, because these members will, the entire truss has to be moved. If it has to buckle in the plane of the truss, then it will be buckling like this. This is the other node. So it will be buckling like this. In that case, in the plane of the truss, you take the distance between the nodes and multiply with 0.7, because what you can say is that only this length is going to buckle. It does not mean that this length is also going to buckle. So this length and the other members here, they will all offer resistance against buckling. So I'll get 0.7 times the distance between the nodes. Okay. However, if it is buckling, if you're considering the buckling in the perpendicular direction, that is in the plane outside or the plane perpendicular to the plane of the truss, or in the direction perpendicular to the plane of the truss, then for that buckling, the effective length will be 1 time the distance between the nodes. Okay, so that's simply from here to here. You don't consider this possibility of 0.7, because then this member, when it wants to buckle, these members will simply undergo twisting kind of a rotation. So that is not very high, that does not offer as much resistance. Plus the gusset plate also can bend very easily in that plane. Whereas for the first one, this one, the gusset plate will have to bend for this to, has to bend in its own plane for this to allow, which is not very likely. But in the out of the plane direction, the gusset plate can bend very easily. Okay, so these are the basic guidelines. There is one example I have solved. This is a very simple example. You must have done similar examples hundreds of times, so I'm not going to elaborate more on this. You can go through this example later. Then there is this interesting type of a system which is known as built-up compression members, which are quite commonly used. Again, railways are the most prolific users of these systems, right? Nowadays, you might see them also for electric line transmission, right? So earlier we used to have this precast, pre-tensioned RC poles, and in Telangana nowadays, everywhere I see only these kind of a. These don't even look like exactly like this. Have you guys noticed what are the structure of electric local electric transmission lines in Telangana, Hyderabad area?
Yes, sir.
So nowadays, what they have is these 4 angles they have. I'm drawing those angles just as a rod, but actually these are 4 angles. And then they have these other angles which are connected to them, right? So likewise, the 4 angles are connected together, right? So those are also built-up sections. So built-up sections can be made. So this is what you have often. These could be lacings, which can be continuous members which are bent, or it could be separate angles or separate plates. Anything can work. So these are all built-up sections. They are quite commonly used for railways, for even the for all the what is it called, the cables which are supply power to the train, electric train. What is that line called?
High tension.
Yeah, high tension lines is okay, although like all the lines are actually high tension lines. Anyway, so you understand what I'm talking about, right? So the overhead lines which supply electricity to the locomotive, all those are supported on similar kind of structures. Okay, so there are various possibilities. You can use channel sections. Railways tend to use a lot of channel sections in this configuration or this configuration and lace together. And often they also use this kind of a tie plates or battens in between. Okay, so these are very commonly used structural systems. What is the advantage of these? Instead of making a hot rolled sections, basically one is that they give very good stiffness in both axes. Right? So for example, a channel has a very good stiffness against buckling in this axis, but you put 2 channels together, now you get a very good stiffness about both axes. Okay, the channel inherently had a good stiffness about this axis. Now you also get a very good stiffness about this axis by putting 2 channels together. Fine. So similarly, so you can increase by placing these hot rolled sections slightly away from each other. You can increase the inertia, moment of inertia, and that's how you can increase the stiffness and buckling resistance. And various kinds of possibilities are there. Now, the design philosophy for such members is that only the vertical members, so these could be the channels here, these could also I sections can be used often. So when you use 2 I sections, you can use 1 I section, and then lace them together. This kind of an arrangement is also quite common for angle sections. So only the members that are vertical, so here these 4 angles, here these 2 channels, and so on, they are supposed to carry the entire load. And lacings and tie plates and battens, they are all there only to hold the members together. That is the design philosophy. So they are only there to hold the members together, and sometimes if the load is applied slightly eccentrically, then distribute that equally between the members, between the vertical elements. Now, what happens, some challenges are here, because when you have this kind of an arrangement, which is not hot rolled section, so it is not continuously connected throughout the length. You don't have to, but as a result, in this plane, when I apply a lateral load in this direction, let's say, generally that is not the purpose of designing these members, but there may still be some possibilities where some lateral load comes in this direction. And if that happens, these arrangements, whatever you had, they undergo, let's say in this particular case, you apply a load like this, these members will be undergoing a lot of shear force demand. Okay, and then this kind of an arrangement is weak in shear force, so you have to be careful against such kind of a possibility. And if there is a possibility of a high shear force or high lateral force acting on these members, then it is better to make more permanent, more stronger arrangement rather than this kind of an arrangement. Okay, because it has a lower shear stiffness. And no matter what kind of arrangement you go for, whether you go for a batten kind of an arrangement or a lace kind of an arrangement, At the top and bottom, you are always required to put some tie plates, which is basically in a form of a batten. So battens need not be that deep. Battens sometimes are also seen of this size. Okay. But at the bottom and top, you have to provide wide enough tie plates to hold the member together so that they don't split. Okay. Different types of different kind of systems can be provided, but they should not be mixed. What it means is that either you go with the lacing system, which looks like this, then the entire length should be done in the similar system. You should not do a mix of this and this. So it should not like up to half a height you come with this lacing system, then the remaining half you do with this kind of a batten system. That is not a good approach. Typically, we should stick with the same arrangement throughout. Now there are certain other guidelines, and there are many other smaller, less prominent guidelines given in the code. You can go to 7611 and get an idea about all the rest. I'm just pointing out a few important ones. So let's say these are the two hot roll sections. AC is one hot roll section and BD is another hot roll section. These are joined together with these lacings. Okay, the lacings are shown here. So CD, AB, and lacings there, of course, are in such a way that lacings are provided only to hold the things together. The entire structural load bearing has to be done by AC and BD hot roll sections. Okay, that was already discussed. Now the way we should put them together is we have to be careful that our RY is this one. Okay, is greater than RZ. Okay, what it means is that if I apply any axial load on this column, it has to buckle. About which axis would it buckle? If Ry is greater than Rz?
Y-axis.
Ry is greater.
Okay, Z.
So it will buckle about Z axis. When it buckles about Z axis, which basically means is that these two members individually buckle about their major axis. Agreed? So even if these were channel sections, these two channels are buckling almost like individually about their own major axis, right? So essentially what you are doing is, if you had provided them independently, they would have buckled about their minor axis. But then from the minor axis, the way you have moved it, the way you have provided the lacing is that now they should actually be buckling about their major axis. Okay, that is definitely going to increase the capacity multifold. Fine. But now, why is this insistence on making the section or individual members buckle in their major axis and not the entire this built up section buckling in the other direction, in the Y direction or about the Y axis? The reason for that is that if the buckling about Y axis takes place, then that will be accompanied by a lot of shear force demand on these lacings. Okay, imagine that this member is bending about Y axis. This is how it will look like. Okay. Then, since there will be some change in the bending moment along the length, you know, the bending moment, let's say axial force P is acting here, P is acting here. So the bending moment will also be having the similar kind of a profile. When the bending moment is non-uniform, what happens to shear force? If the bending moment is uniform through the length, what is the shear force value?
0.
0, right? Shear force is nothing but the gradient of bending moment. So if bending moment is uniform, there is no shear force. But if the bending moment is non-uniform, that will be the case now in this situation. There will be some shear force demand in the members. And what will be that shear force like? That shear force has to be resisted by these lacings. And these lacings have to be designed for that shear force. So if we don't want to do that for pure compression, we don't want to have to deal with that situation. So that we don't want any deformations in this axis. So what do they do? What do they say? They say that you make in the configuration in such a way that your RZ is smaller than RY. Then when the column starts to buckle, or let's say buckles a little bit, then the deformed shape will be not in this axis, but in the perpendicular axis. I don't know how to draw that or how to differentiate between this and that. So the buckling will be in such a way that this part extends and this part contracts, or the vice versa. But in that situation, the lacings are provided in such a way so that they can very easily extend and accommodate that. You know, this is kind of this Caesar system, right? So when you stretch, if I stretch this part, if I want to stretch both of these parts equally, then the lacings will very simply accommodate that deformation. The two parts will come slightly closer and lacings will deform. without introducing any stresses. But if I stretch this part differently and this part differently, then the lacings will be under stress. So that's what they are saying. So if I make sure that the buckling happens in such a way that both C and D undergo compression and both A and D undergo elongation, then these lacings will not be stressed. Okay, and all the shear force will be transferred through this web, which anyway was designed to carry a lot of shear force because this was a hot rolled section. So they have a lot of shear strength. Then there won't be any issue. That's why this insistence on Ry being greater than Rc. Okay, I think explained it in quite a bit of detail. If you still find it difficult to follow, you can hear back this introduction. You can also go to the textbook and try to follow. And otherwise, you can ask me a question in the next class. I'll try to explain it again if you find it difficult to follow. Okay. Still, the lacings, even though they are not supposed to resist, you make sure that there is not much shear force demand, or there is not much force demand on the lacings. Still, there may be some accidental load requirements. You may accidentally be applying some lateral load on this system. Some kind of a lateral load could be acting, and that has to be resisted. So if you apply any load like this, that will introduce some kind of extension here, and contraction here, or tension here, and compression here, right? And that tension compression combination will lead to some force coming onto the lacings, and the lacings have to be designed for that kind of a force. So what it says is that whatever the axial load for which the column is being designed, you take 2.5% of that axial load, apply that laterally, and solve it as a truss. Imagine that this is a truss and this kind of a load is acting, and then calculate what is the member force that will be coming onto these lacings, and design these lacings for at least that much of member force, which is typically very small. And most of the times you have some thumb rules which you can follow to make sure that these lacings are strong enough. Okay. Otherwise, if you know that there is going to be a significant amount of shear force coming and still you want to go with this kind of an arrangement, then for that shear force, then you don't worry about 2.5%. If you know that there is a significant force coming in, so at least 2.5% or whatever is the actual shear force coming in, for that you design these lacings. Okay. And also when you calculate the buckling load capacity about this axis, see about this axis it is fine because you have made sure that this is a hot rolled section buckling. But when you talk about, let's say I have 4 angles, then all 4 sides I have got the lacings, right? Then I don't have a choice. It is going to buckle about one axis or the other. Even if it buckles about this axis, some of the lacings, these 2 lacings are going to go under some kind of a force demand. So then for that one, you because the lacings are weak in shear, they do not lead to, basically when something is weak in shear, we do not satisfy the requirement of plane sections remaining plane. That means if you consider this neutral axis, if this is the neutral axis in this situation, and these are the 4 angles that we had. So about when the buckling takes place about this neutral axis or bending takes place, the stresses or strains at each location will not be exactly proportional to the distance from the neutral axis. Okay, and that the reason for that is that these bracings are weak; they are not very stiff. Okay, and as a consequence, you will not have linearly varying strains. So because of that, your deformations will be larger than what your assumption of elastic beam theory presents. So what it says is that instead of taking L by R, you take 1.05 times L by R. So you take additional 5% R L, or reduce your R value by 5%. Either way, you can look at it either way. Okay, so that will be the additional flexibility in the system that you need to consider, and that's how you calculate the buckling load capacity of the combined system. Another thing is that this lacing pattern should be identical on the 2 sides. So you have lacing on this side and you have lacing on the exact opposite side. These are the 2 channel sections. I have one set of lacings here, one set of lacings here. The way they should be arranged is that if you look from one side, from the front, you will see a lacing system like this. Okay, the lacing system on the back side should be a copy of this one, and it should be such a copy that you should not be able to see that if you're looking at this one. So the one behind this should be hidden behind this one. Okay. So if I can project it back, so the one behind this should exactly follow the same pattern. You understand? Right? So it should be right behind the front one. The idea again is that if there is going to be any elongation or uneven elongation of these members, these bracings should be able to accommodate that without getting subjected to a very large force demand in the bracings. And that is possible only if you do it this way. If you create an offset, right? So for example, in the front side, this is how the bracings were. And on the back side, instead of following this pattern exactly on the back side, if I go this way, I've created an offset, right? So, or exactly opposite of this one. So if I do this kind of a bracing on the back side, then what will happen is that it will not allow the extension or tension or compression of the main legs without introducing any forces in these bracings. That has to be avoided. Okay. And then there are limits on what can this angle be. So this angle has to be between 40 to 70 degrees. It should not be less than 40 or more than 70. And the slenderness for these members should not be less than 145. Okay. Again, these are not really designed for much force value until you have very large shear force demand. Until you are in that situation, you don't have to really design these lacings. You can simply go with some thumb rules. As long as you make sure that these are within 145 and some thumb rules are followed, you are okay. So with this, I think this discussion ends. Any questions up to here? In the next class, I would talk about fire behavior of structural systems.
So,
Yeah, Leo.
in the batten column, batten like type, instead of lacing, they're batten using now. And
Yes.
in that, there's something 1.1 kL. So 1.1 instead of in lacing is 1.05. And
Okay.
so is that 1.1 also that additional is accounting for
Yeah,
shear?
actually, correct. So I have not copied everything from the code. There are a large number of provisions. Maybe I have because even I cannot remember all individual guidelines. Let me check. So basically, the idea here is just to communicate to you the principles of these things. Now, of course, the battens you can understand is that they would have even lower shear stiffness. Yeah, so the effective slenderness ratio for batten column shall be 1.1 times. Yeah, so instead of 1.05, 1.05 was for the one with the lacings. The one with the battens should have 1.1 times the KLR. Thank you. Yeah,
Okay.
I agree. I have not copied everything from. There are a number of provisions. I've taken only some guidelines.
Okay.
I've only taken the ones which are sufficient to explain the fundamentals. You
Okay.
should of course go through the code and go through the textbook, because I cannot cover in the class every single provision. But thank you for pointing it out.
Thank you. Thank you.
Anything else? All right. So thank you guys. So next class we will talk about fire design, or maybe I'll see which portion I'll pick first. Maybe the base plate design if I am ready with those lecture notes. I have not shared those lecture notes with you yet. So maybe I'll share the fire design or the lecture notes first, and then we will discuss that. And by the time I'll get the base plate design lecture notes also ready.
Excuse me, sir.
Yeah, Aditya.
Sir, why can't we use both lacings and battens together in a single column?
Yeah, the idea is that they have different shear stiffnesses. Okay, so if you mix them, what will happen is that the one that is more flexible will attract most of the force, lateral force. So most of the deformation will be confined to that area. So there, and you want to maintain a uniform shear stiffness throughout the length. If you mix the two, one of them will contribute more, and all the deformations will be accommodated there only. Okay.
Thank you, sir.
So that is also a reason why we never weld and bolt something together. Okay. So, I mean, we do, but there is a difference. I'll give you an example of welding and bolting. Okay. So, how should I start? You have a beam. And let's say this is an angle that is welded, that is connected to this beam, and it is connected to a column here. Okay. Now we can weld this angle to this column, and we can bolt it here. That is allowed. But what we are not allowed is to, let's say it is welded here. That is fine. Here, let's say I calculate that my load requirement is 100 kilonewton. And what I find is that my one bolt has a capacity of 25 kilonewton, or let's say 40 kilonewton. So what I cannot do is I will do 2 bolts, I'll get 80, and then I will also do a weld. That will give me another 20. That is not acceptable. Okay. Whatever force transfer has to be done here from this member to this member, that entire force transfer either has to be done through welding or has to be done by bolting. So the bolts should be able to resist the entire load by themselves, or the welding can be done and the welding should be able to resist the entire load by itself. The reason for that is that both of them will not reach their full capacity at the same time. So if I do this kind of a loading, this kind of a arrangement, that there is some welding and some bolting, and if I want to, if I start applying the load on this one, okay, I start applying this load on this member, and I monitor how much load is being carried by the 2 bolts and the weld. So what will happen is that since the bolt and the weld, they have different stiffnesses, weld is much more stiffer, so it will carry most of the load. So initial, I start applying the load. Let's say the weld has a capacity of 20, and both bolts have a capacity of 40 each. Okay. What will happen is that the weld will pick up the load very quickly, and it will reach its load resistance of 20. But at that time, the bolts are still slacking. Okay. So the 2 bolts together should have reached 80 at this time, but when the deformation is this much, the bolts are carrying only this much load. And what will happen to this weld after that? If I keep pushing it, weld will fail. So weld will maximum resist its 20 kilonewton, whatever it was supposed to do, and then it will fail. And by the time bolts actually start playing a role, so this is this deformation, and the weld has gone. Now the bolts will also not have the company of the weld to resist the load. So when you have 2 systems which have very different stiffnesses, you don't combine them. You don't combine them to resist the same load. However, this was perfectly okay if I had this kind of an arrangement. You do the welding here and you do the bolting here. You had total 100 kilonewton. The same 100 kilonewton you were able to resist with these 2 bolts because each had a capacity of, let's say, 50. So then you could do this, and this weld you can provide, which itself has a capacity of 100 kilonewton. You are able to resist 100 kilonewton by these 2 bolts. These bolts are transferring the load from the beam to the angle, and then this weld is transferring the load from the angle to the plate, to the column. That is okay. Similar logic holds true here. When you mix lacings and battens to the length, for certain length you use battens, certain length you use lacings, then the 2 systems will not really reach their peak capacities at the same time. So when the one part is loaded, the other part will not be loaded much. Okay, I hope I explained.
Yes, sir. Thank you, sir.
Yeah. Any other questions? Lohit?
I mean, it's related to foundation, sir. I will ask him when you explain base plate. When
Sure.
you explain base plate, I will ask him.
Sure. All right then. Thank you, guys. Yeah, please try to install it. If you are not able to install, you can write a comment here, and then Krishna can follow. You can try calling up that guy and try to figure out what's the issue.
Okay, sir. Sure, sir. Thank you, sir.
Bye.
Thank you, sir.
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 Thanks. Bye.
Thank you, sir.